Welcome to this instructional video to move the notes forward in Chapter 4. We were talking about beta sheets, and we showed an example here in class of an anti-parallel beta sheet. And our bottom line was, when it comes to side chains and the stability of a beta sheet, we have to really consider inter-strand side chain interactions. So what we said was, I think the example that we left off with was right here, position A and position D. In position A, you could have an arginine positive. In position D, you could have an aspartic acid negative. That would significantly stabilize the structure of this beta sheet. But amino acid side chains on the same strand, intrastrand, just aren't possible because they're not really that close to one another. That was the take-home message. So what you need to be doing is thinking about, what could be in positions, again, the alphabet, not the one-letter amino acids, the alphabet, position A and D, and then E and B, and then F and C, because those are the proximity positions that are close to one another. So what can we do? We saw in class today an amphipathic alpha helix. Wow. So do you think it's possible at pH 7, let's say, to design an amphipathic beta sheet? I think that's possible. Let's do this. So let's design. In fact, you're going to become in Chapter 4 protein designers. You may even get your own show on HGTV. So, you're going to be designing protein structures that meet certain criteria. I'm not talking about shabby chic design or mountain industrial. We're talking about protein design. So let's see if we can do an amphipathic beta sheet. So we know, just like a helix can have two faces, a beta sheet clearly has two faces. And even though it's not flat and planar, in class I showed you it was typically a little bit twisted. There typically are two faces in a beta sheet. So, and we also know that the side chains alternate up and down, if you want to say it that way. So let's take an anti-parallel beta sheet. So we have two strands, the black strand and the red strand, and we want to make one, let's just say the top face, let's make that polar. Yeah, let's do that. And then let's make the bottom face, nonpolar. So that would be amphipathic beta sheet. So let's just start our design. Let's start off here with a phenylalanine. And then, so I'm starting with a nonpolar at the bottom because that's what we said we wanted to do. There's a lot of possibilities here. I'm just giving you one. But lysine is positive, and then we're going to go alanine. Then we can go aspartic acid, and then we might go isoleucine here. Whoops, hang on a second. We're only doing the black strand now. So we got to go here. We need a valine, and we need a polar amino acid here, Q, and let's just end it with W. So I just did the amino acid sequence in the black strand that would be able to be a part of an amphipathic beta sheet. So we have to make the strands amphipathic is the key, I guess, right? So let's go on the the red strand. The red strand, if I want to start off here, I better make this nonpolar. So there we go. We can make this an E, which side chain of E, which would be negative. Now let's recall, we would have this would be ionic here, and that's going to really help stabilize our beta sheet. But the K and the D over here are not close enough to interact. Okay? Let me emphasize. when it comes to stability or lack of stability, we have to consider inter-strand side chain interactions. But let's keep making our amphipathic beta sheet. We could make this isoleucine perhaps. Then we need to go up here. Again, I'm moving along the red strand, by the way, right? So now we need to start. We started nonpolar, then we went polar, nonpolar. So let's just go polar. Wow, that'd be a beautiful hydrogen bond between D and N. What else can we do? Oh, let's use methionine as a nonpolar. And let's go with just a serine here with polar. And then we ended up with alanine. So I'm not going to take the time to go through all of these side chain interactions. This would be H bond, a charged H bond. Wow, that's pretty cool. And then here is just to be a H bond. And probably down here, I'm not going to draw it in, but we would maybe have some dispersion forces kind of helping stabilize the beta sheet. But definitely this is amphipathic, and so this amphipathic is in my way, so I need to move it. I'm going to the bold marker. That's been a problem in the past in this class, but let's do it anyway. This is non-polar face, and this is definitely a polar face. So some beta sheets can be amphipathic. I'm sure this will come up again in this class, but let's go ahead and kind of move on. So what we want to do next is talk a little bit about the beta turn, a very important component of soluble protein. So really our main focus with the beta turn is going to be soluble proteins. Proteins soluble in water. And proteins that are soluble in water are roughly spherical in nature. So they have to, to say it unscientifically, ball up, be in a ball, a sphere. And then the technical term, I guess, is globular proteins. So the backbone has to have a lot of abrupt turns. And that's what we're talking about. Technically, there are two types of beta turns, type 1 and type 2. I don't really go into the detail about the difference with these in this class. I just want to give you kind of the highlights that could apply maybe to both of these. So here we go. We're moving amino alpha carbonyl, amino alpha carbonyl, amino alpha carbonyl. So we're moving this way, and then the backbone has taken a turn. There's the carboxyl terminus. So we've kind of made an abrupt turn to allow these globular proteins to kind of form a spherical globular shape. Well, here are some structural aspects about these that we need to talk about. Number one, this shouldn't shock you, backbone hydrogen bonding. There's one backbone hydrogen bond in the beta turn. Now, what is the arrangement of amino acids? In the alpha helix, backbone hydrogen bonding was N plus 4. Well, let's do that here. Let's say this is amino acid N. There's the carbonyl of amino acid N. This is N plus 1. This is N plus 2. This is N plus 3. So it looks like the backbone hydrogen bonding in a beta turn is N plus 3. And again, this looks like an ideal hydrogen bond. All right. Does that stabilize the beta turn? Yes, it does stabilize the beta turn. All right. So issue number 2, proline. We haven't said a lot about proline, except it being a kind of a helix breaker, because proline is very prominent in the N plus 1 position of a beta turn. And that's typically where you find it. And then, if you keep going along here, amino alpha carbonyl, amino alpha carbonyl. It is the natural kink in proline. Proline has a cyclic side chain, and that affects the backbone, and it causes a kink in the backbone of proline, and this kink fits the beta turn. It does not fit the alpha helix, so it promotes a turn, not a coil. All right. Same thing with the backbone hydrogen bonding. If you have N+3 backbone hydrogen bonding, that promotes the turn, not a coil. We are turning, not coiling. That's a very important distinction. Well, the third issue is glycine is usually in position N+3. So this is issue number 3. So let's look at this. Here's a side chain from the amino acid in position N+3. Here's the side chain in the position N of the turn. It may not look like it in this image, but those R groups are kind of projected toward one another. So you need one of these positions, and it's usually N+3, to have a really small side chain. That will help stabilize the beta turn. Imagine the R group for N and the R group for N+3 being, even alanine would be somewhat problematic. What if it was 2 valines? That would disrupt the beta turn. That would be a very big problem. So here we go. We know glycine doesn't promote the coil, the alpha helix. It promotes the turn. So the small side chain prevents a steric clash with side chain in position N. The side chain in position N. So that's what we have here for a beta turn. We need to turn the backbone, not coil it. We need to turn it. And so we have 3 important considerations in beta turns. Now, something you're going to see sometimes is what we call a loop. What is a loop? Well, here's a loop, and here's a loop, and oh, look at that. That looks like a loop. And a loop really is, let me define it this way. Let me see if I can kind of change colors here. It's random structure between secondary structural elements. And it may contain a beta turn. It doesn't have to, but oftentimes it contains a beta turn. So this right here is kind of a beta turn. Now this whole loop is not the turn. The loop is random structure between secondary structural elements, and it might contain a beta turn. This looks like a beta turn. So beta turns may be part of loops. They may not. Or you may not even need a loop. But a loop is something that's, let's just call it random, but it may contain a defined structural element that we call the beta turn. So we'll see loops as we go along, as we move forward. So we're talking about, really right now, soluble proteins. Proteins that are soluble in water. And then they have secondary structure. It's typically the alpha helix, the beta sheet, or the beta turn, or you can have random as well. So here's just an example of a soluble protein. This is human thioredoxin. This is involved in electron transfer in us as we speak. I'm just showing you, as this is a model protein. Can you see the alpha helical regions? I think so. Can you see that beta sheet? I think so. Can you see some turns? I think you can. Can you see some loops? Well, I think you can. So it's all kind of in there. Back to this beta sheet. This is a mixed beta sheet. It's a little bit hard to see, but that's what we have. And it definitely shows, as I said in class, the twist, kind of a twist nature of the beta sheet. This protein down here is human serum albumin. All of us have this in blood serum. It is kind of like the Uber to carry fatty acids in the blood. Fatty acids are not real soluble. They need a transport protein, and so human serum albumin transports fatty acids. Well, look at human serum albumin. It doesn't have any beta sheet. Is that okay? Well, yeah, that's okay. So this is what we would call an alpha helical protein. Now, there's turns in here, yes, but there's no beta sheet. So typically we might use the term alpha helical protein or beta sheet protein if there's not one example of a helix or a beta sheet. And so most proteins have some of each, but human serum albumin does not have any beta sheet, no beta sheet, and that's okay, because this structure of HSA, human serum albumin, fits its biological function. Now, so if you want to know some typical, well, if you want to know some examples of how much alpha helix is in a protein, how much beta sheet, or they call it beta conformation, then you can kind of look at this table. There's nothing to remember about this table except there's no set percentage of either one of these in a protein. Ribonuclease has 124 amino acids. 26% of those are in alpha helix. 35% of those are in beta conformation. I believe that's beta sheet, and that might include beta turn, but it doesn't really matter. There's no set percentage for this. Cytochrome C. Look at cytochrome C. It's another example of a protein that has, okay, let me back up. I'm sure this is not including beta turn. This is just beta sheet. Just beta sheet. Because there's no beta sheet in cytochrome C. Myoglobin. We're going to talk about myoglobin. We're going to get really detailed about myoglobin. It's an alpha helical protein, no beta sheet at all. So there's no set percentage for alpha helix and beta sheet. The structure just fits the function. All right. Well, as we move forward with soluble proteins, this is a very qualitative description of how these proteins fold. We're going to get more quantitative after we talk about fibrous proteins. But let's just take this image. This is a very good image or graphic of an unfolded polypeptide or protein. And again, we have to remember, and I'm getting nervous about this, about having to do this, we have to remember that this is done in water. So I'm not going to actually put the dots because I don't, that's been problematic before. So just remember, and we will talk about this later, there is water surrounding this unfolded polypeptide. Okay, and then when it folds, there's water all around it. So we cannot ignore the role of water in protein folding. It is crucial. But all I want to talk to you now is the distribution of amino acids. The blue amino acids here, as the graphic says, and it may be kind of hard to see, the blue are polar side chains, and you should know which ones are polar. And the green side chains are nonpolar. Now I'm going to give this a big U for unfolded. And I'm going to give this an F for folded. So this is an equilibrium. So you have an unfolded polypeptide or protein in water, and it needs to fold into a defined three-dimensional structure intimately tied to its biological function. And the rough, I guess, rule of thumb here, and I think this makes perfect sense, is that typically you're going to find polar amino acids on the outside because they like water. And then you're going to find the nonpolar in what we're going to call a nonpolar core. And again, that's where the nonpolar amino acids, the green ones, are at. Those are the main amino acids there. So one of the driving forces of protein folding, we will see later, is moving hydrophobic side chains. Think about valine being surrounded by water and all those caged waters. Valine doesn't like water. It's hydrophobic, water-hating. So this protein will be driven thermodynamically toward the folded state, where we have polar amino acid side chains on the outside, mainly nonpolar amino acids in a core, mainly. What we do know, one little exception to this, and I think this is important to know, is that you might find some uncharged amino acid side chains forming hydrogen bonds in the nonpolar core. And we might, we know ionic interactions are stronger when you have a lower dielectric constant. And oh, by the way, the nonpolar core has a low dielectric constant. That's why I've been asking you all these questions up till now. Okay? So, the nonpolar core can have other things. It's probably not going to have that many ionic interactions because the side chains have to be charged, but it definitely can have some uncharged amino acid side chains forming hydrogen bonds. And what comes to mind? The major players S, T, Q, and N for sure. I think those will be major players in that. So this is kind of just a rough example of protein folding. Now, at some point in the class, I'm going to show you structures of proteins, and we're going to color them by polarity. And I'm going to take a molecular knife and I'm going to slice in the middle of them. And when we do that, we're going to see this representation like we have of a protein called lysozyme. It's an enzyme, but it's a protein as well, so let's just call it a protein. The nonpolar core is going to be represented in gray. So when we start doing this color coding, and we will do a lot of this, gray equals nonpolar side chains. And the pink or the purple, however you want to say that, pink/purple, will be polar groups, polar amino acid side chains. And you can see that this graphic here, this image right here on the right part of this page, says or demonstrates clearly that this soluble protein, when you slice into the center, has a lot of non-polar amino acids. That is very clear. And most of the polar amino acids are on the outside exposed to water. Again, this is a prelude to us talking about this probably over and over and over again. Well, how do you stabilize a folded soluble protein? Well, we can kind of get into some interactions that are going to help stabilize proteins. And so What we're doing here really is talking about side chain interactions in this protein lysozyme. So let's look at a few examples. This is the side chain of the amino acid arginine. Let's assume we're at pH 7, of course. And this is the side chain of the amino acid aspartic acid. So arginine and aspartic acid. This is an example of an ionic interaction. But I'm going to need you to tell me what level of structure is being solved. Being stabilized. So this is an ionic interaction stabilizing tertiary structure. Now, how do you know that? Well, I can tell from this graphic that the D and the R are not near each other in the linear sequence of amino acids, yet they are brought together in proximity in the folded structure. They are not both on a sheet or both on a helix. Therefore, they're stabilizing tertiary structure. Okay? And so what we're going to practice and get good at are looking at certain types of interactions that stabilize secondary structure or stabilize tertiary structure of a protein. The only possibilities in what we're doing now is using side chains to stabilize secondary, tertiary, or quaternary. Now, quaternary, this protein does not have quaternary structure. So really, I'm just focusing on secondary and tertiary. Why did I say the D and the R are stabilizing tertiary? Because they are basically brought together. They're not close together in the linear sequence. They're not on a helix. They're not on a sheet. They're not on a turn. So they're stabilizing the tertiary structure of the protein. Now, how could I show you a secondary structure? Well, what if I'm just kind of making this up now. Let's say we had a Q and we had an N right here and kind of a 1,4 relationship off this helix. Wow. There we go. This would be a hydrogen bond, and since they are on the same alpha helix, they would be stabilizing secondary structure. So this Q and N on this protein or on an alpha helix, that's secondary structure. They're probably, I'm telling you, they're in a 1,4 relationship. They're near one another. I'll just write 1 and 4 just to say 1 and 4 relationship. They can form a hydrogen bond. Is that stabilizing this protein? Yes, it is. What level of structure is it stabilizing? Secondary, because they're on an alpha helix. Okay? Now, these gold bars here, and I'm going to use orange just so you can see it. There's a bunch of these gold bars in lysozyme. This is really showing you our old friend, the disulfide bond. So here's a cysteine. Here's another cysteine. They are brought together. They're not in the linear sequence of amino acids, but they get together when the protein folds. They react. This is not interaction. This is reaction to form the disulfide bond. And so in this case, all these bars here are showing disulfide bonds that stabilize tertiary structure. You can see one right here. You see kind of a random part of the structure forming a disulfide with the alpha helix. Well, that would be, again, a disulfide stabilizing tertiary structure. All right. Again, I'm doing a video over this because we're going to review this as we move forward with protein structure, but this just kind of lays the groundwork as we move forward. Something very important that we need to talk about next is that proteins, to do their job, oftentimes have to bind ligands. And a ligand is a molecule, and for now, let's just call it a small molecule. It doesn't have to be, but for now, let's call it a small molecule that binds to a protein. So proteins have ligand binding sites. That's exciting. Ligand binding sites. And so there's three different types of sites. So let's look at this. The little green monsters here are proteins. And the red shapes are ligands. We are forming protein ligand complexes. All right? And so this page is to demonstrate that there's three kind of general types of ligand binding sites. They can be a pocket, kind of a deep pocket for the ligand to fit into. And this is demonstrated here. This is a protein. In this case, it's a little hard to see maybe. The ligand is kind of green in color right there. But what are these blue residues? What's the blue? This is the ligand binding site on the protein. And this looks more like a pocket that the ligand can just pop into and fit into. If the ligand binding site is more of an extended thing, and it's still kind of deep and extended, we would call it a groove. If it's deep and not really extended, it's a pocket. If it's deep and extended, it's a groove. If it's shallow and extended, it's called a surface. A surface. And all of these rely on what we call molecular complementarity or molecular recognition. All right? So let's review what we're talking about here. This is not a new concept to you. I'm just repackaging it in terms of ligand binding to proteins. Now the surface, real quick before we go on to that, the surface really is what we've been talking about in class. It's ridges into grooves. This is a ridge. This is a, wait a minute, I think I got that backwards. Don't get your ridges and grooves mixed up. That could be bad. So I think this is, if we, well, here's the deal. Let's be careful with this. This is a groove. This is a ridge. And this is a groove. Okay? So, up here, we have a ridge, a groove, and a ridge. Look, when these two things come together, we're going to have ridges into grooves. That's called shape complementarity. And not always, but this is usually dispersion force driven. And it depends, the strength of the interaction will depend upon surface, you've heard me talk about this, surface area. So this is a great example of ridges into grooves. And it usually is a surface phenomenon. Surface phenomenon. If you want to call it interdigitation, this is kind of like interdigitation. This is a very, very good way for two surfaces to interact. So the surface of the ligand will bind to the surface of the protein, ridges into grooves. Hey, we have binding. Now, don't think shape is the only thing. When a ligand binds a protein, whether it be a pocket, a groove, or a surface, there's going to be charge complementarity. And this can certainly be ionic. And then we can also put in hydrogen bonding here, right? Now, hydrogen bonding is interaction between partial charges, and ionic interactions are between full charges. But we can still call this charge complementarity. And so what we're going to have to get used to thinking about are molecules binding together. What governs the binding of two molecules? Shape complementarity and charge complementarity. Those are going to be the major drivers of something we call molecular recognition. Let me give you a little bit of an example. Let's say we have a carbohydrate. This is your old friend glucose. It's polyhydroxylated. Glucose is a ligand for many different types of proteins. Again, let's just say we're at pH 7 to be very clear about this. Now, how could a protein, which amino acid side chains in a protein might be involved in binding glucose? Well, here we go. Here is a protein glucose complex. We have glucose binding to proteins, and you're seeing a bunch of different amino acids here. Okay. Now, the first thing we need to get straight, and you need to think about this. You should, when I ask this question, you should pause the video. You should answer the question and see if you get it right. At pH 7, will glucose be charged at pH 7? Well, hopefully you're right about this. Glucose will not be charged because you have molecular literacy. You know that these hydroxyl groups, which are ionizable, I got you, I'm with you, they're ionizable, but they're pKa's. Wow. You know, what are they? You know, probably like 13 to 16 or something. So at pH 7, they're not going to be charged. So we're really probably talking about hydrogen bonding between glucose and the protein. And so I'm going to give you 3 examples. Okay? I'm going to put an A right here with this hydrogen bond. And A is an example of a charged hydrogen bond between this protein and glucose. That's what it's showing you right there. Lysine has a charged side chain. It is forming a charged hydrogen bond with glucose. That's a great demonstration of that. Well, B, let's see. Oh, here we go. Here's B. I put B next to asparagine here. And that asparagine is forming just a good old traditional hydrogen bond. Can asparagine be charged? Of course not. Surely we got that under control by now. So this is just a good old hydrogen bond. Is that helping glucose bind to the protein? Yes, it is. It is helping glucose bind to that protein. Okay? And then let's do one more. Let's do C. It looks like there's a water. Look at the water molecule here. You can have water mediated hydrogen bonds between proteins and ligands sometimes, especially between ligands that are very polar, like glucose, that are not charged, and protein side chain. So it looks like, you know, we really look at this figure closely. We have what we would call hydrogen bond networks, especially for C. You got glutamine 11, hydrogen bonding with water, and that water is hydrogen bonding with glucose. That's what that's showing you. Okay, so you need to get in your mind between proteins and ligands, we can have hydrogen bond networks. Now, the ligand in this case was not charged. If it was charged, we'd have some ionic interactions, and we'll get to that. But for now, I've just showed you a molecule of glucose binding a protein, and look at all these amino acid side chains that are involved in recognizing the ligand. In fact, there's more than one water-mediated hydrogen bond. I just showed you one. I mean, look at, I just saw another one in here. This caught my attention. There's one right there. Look at that, threonine 147. The side chain is forming a hydrogen bond with a water molecule, and that water molecule is forming a hydrogen bond with glucose. It's also forming a hydrogen bond with the backbone atoms of an aspartate residue. That carbonyl there, I believe, oh, that may be the side chain. No, look at this. This is very, very, very informative. If you look at this aspartic acid right here, this is the side chain. This is showing you backbone atoms of aspartic acid. Remember, backbone atoms can be involved in hydrogen bonding if they're not involved in an alpha helix or a beta sheet. There are backbone atoms from proteins can form hydrogen bonds with water or ligands. All right. So let's do one more page. This is an example of a binding pocket in lysozyme, and there's a lot going on in this figure. The ligand is blue. In this case, we're using a different color scheme. I'm sorry, but that's the way it goes. This is the ligand in blue. And here, the ligand binding pocket is green. And again, this is just these are the same thing. They're just different renderings, different representations. So this ligand is binding to the this lysozyme ligand is binding in the ligand binding pocket. It's a very well-defined pocket. And this, I think, really, we'd have to look at it a little bit better, but I think this is a surface. And so we need to know the structure of the ligand. We need to know the amino acid side chains in the ligand binding pocket to really understand what type of interactions are involved. But I can guarantee you one thing, is that there's shape complementarity. And you can kind of see that a little bit. There's shape complementarity, and then I'm sure there's also some charge complementarity, either ionic, or if the ligand's not charged, hydrogen bonds. So that's going to help what we called molecular recognition. Now, things we're going to encounter as we move forward in this class are two things. Two other things. Binding specificity. There's a protein, let's do this. Protein binding specificity. If you're a protein, do you bind just one particular ligand? Do you bind a couple of ligands, or are you promiscuous? Are you a promiscuous protein? That's my question to you. Do you bind a lot of different ligands? We see all types. So we're going to have specific binding, selective binding, and then promiscuous binding. We're going to see all the three types when we talk about different proteins. So specificity is key, okay? Is one key. The other thing is binding protein, binding affinity. Select specificity and affinity are two very, very important aspects of protein binding ligands. If you're a protein, do you bind your ligand tightly or do you bind your ligand weakly? That's going to be very important in your biological function. So I've used this video to move us into soluble proteins, just to kind of lay the groundwork for some of the nomenclature and some of the big ticket items. On Friday, we're gonna kind of switch gears, talk about 3 fibrous proteins, and then when we get done with that, we will kind of shift back to soluble proteins and really get into some detail of how do proteins fold into their defined 3-dimensional structure that is intimately tied to their biological function. That's it for this video. Thank you.